Yeah. Hello everyone. My name is Rajesh Sharma. So today I am here to give you a demo for my thesis project. So the topic of my project is estimating remaining useful life and state of health of EV batteries via hybrid physics informed deep learning frameworks. So this thesis is done under the mentorship of Dr. Sandeep Patale sir. So let's start with some introduction and problem statements. The problem is this: the battery degrades and it degrades non-linearly, and battery management system must estimate health and remaining useful life accurately. The data driven models are accurate, but they are physically inconsistent, and it requires too much data set or data, so which make them incompatible for edge deployment or standard BMS chips, battery management chips, or like microcontrollers like Cortex M4. Physics models are interpretable, but they are too slow. They are also using PDE, partial differential equation. My solution is the small GRU networks with whose loss is regularized by battery degradation or ODEs, ordinary differential equations. The target is on board deployment or edge deployment on the chips like Cortex M4 and other standard BMS microcontrollers, which uh, which which has only 1 megabyte of flash memory or less than that. So let's proceed. The headline of results are simple. The hybrid model get the lowest error from the 10 comparable models in same environment. The matched control proves that the gains come from the physics, not from the size. And the deployable model needs only 20 kilobytes, which is the fraction of the memory if we consider M4 Cortex as a microcontroller chip in BMS. Everything is here is use Python. The versions are written here. So the core framework are PyTorch 2.51, and it handles the model, the physics autograde, and the int 8 quantization. The NumPy and Pandas use handles the numerical and the data frame and the tables. Where SkyPy does the curve fitting and the other statistics. Scikit-learn provides the scaling and the SVR baseline, matplotlib used for figure and visual representations and graphs. Where Optima 4.9 runs the Bayesian hyperparameter search. There is no TensorFlow, no LangChain, and Hugging Face. Like this is not an LLM project, so I have not used that. Everything runs locally on my laptop. It is an Apple M2 with 8 cores and 8 gigabytes of RAM. No GPU is needed or used. This is the design point. The thesis is about the model small enough that runs on embedded devices or hardware or edge devices. So the CPU is enough. The dataset is 176 megabyte, and complete end-to-end run takes around 20 to 25 minutes. So this is the dataset required. I use two public dataset with lithium cobalt oxides. The NASA dataset has 4 cells and with 636 labeled discharge cycles, where in raw MATLAB files, where the Kelsey dataset has one cell with 878 cycle, and this is the regression task. So no classes or no tokens, and the label is per cycle state of health. RULs come from the 80% threshold with a consecutive 5 cycle persistent rule. This is the standard definition of RUL. So we are taking this in this thesis. So in pre-processing includes time step ordering and MD5 confirmed duplicate removal, outlier filtering, and 8 engineered feature per cycle. The split leave one cell out whose the whole cells never mix, and scalar is fit on training cells only, so there is no leakage. That's reason I talked about this. Each fold is run with 3 seats, and this is the tool and exhaust the environment. Every everything runs on PyTorch on CPU, fully local, no cloud and no API. And the quantization use PyTorch dynamic intent, and the size are measured, not estimates. The deployed model is exported to ONNX, and here is the implementation is one self-contained notebook with 59 to 60 cells. Every function is defined inside, so anyone can reproduce every number of it, plus the row who have the notebook and the row data, and everything is like saved in a local file, like the tables and figures. This is the pipeline design. So I have divided this whole project in 5 phases. So first we some data foundation, then we feature extraction, then model evaluation, and then at last we deploy. We check that hardware profiling and other stuffs like memory footprints. So let me go walk you through the code itself. So here's the setup cell. It prints the library versions, and yeah, this one. It prints the library versions like NumPy, Pandas, so, and the directory output directory addresses as well. And this we can check it. We can also run it. Yeah, so this is the NASA dataset. So you can check like these are the features we have with NASA cell. So there are 4 cell series, B005 and 006, then 7 and then 18. Then then for KLC dataset. This is it tells a lot about data. So here we did some plotting to check the different cells of NASA dataset. Here's the and the feature after this is the KLC dataset. So after this we filtered, or we did filtering with the help of Satwick-Golway filtering. So this is the phase 2. First phase is we are doing some EDA only, and then for features we extract the features and then do Satwick-Golway filtering before the autograde that differentiation, because we have to do filtering, because if because of noise of data, it can lead to some differentiation issues, like it can spike differentiation, or it can show some uneven numbers, because the noisy data we can't do directly differentiation. So here's some feature extraction we got from NASA dataset. So this is the feature correlation matrix also. This is consolidate cell wise data with other constants. We going to use it in this file. This is cell wise data. For Kelsey we have only one cell, but it is like a long data set. Yeah, in training there are 10 models. A curve fitting as an SVR as a floor, then GRU, LSTM, 2 transformers, and neural OD, then matched capacity control, and then 2 hybrid variants. The physics enters the loss not as an architecture. This class is the center of the thesis. The Verhulst ODE residual and autograde computes the derivative of predicted health with respect to the cycle coordination. The loss is penalized its derivation from r and y times, which is the constant I'm talking about, these constants. So for training I use Adam optimizers, and learning rate is 0.02. So batch size is 64 and 128 epochs. Early stoppings at an patience of 15, and the benchmark hybrid has 41,000 parameters, and deployed has 11,000 parameters. I will show you later when we do hybrid profiling. So these are the models. So there are two routes. So let me show you. The full evaluation is 4-fold times 3 seats and 10 models, which takes about 20 minutes. So I show the saved outputs. The route B wins. Let me show you the results. So it took time, so that's why I show you the saved data. So here's the evaluation we did. Sorry, this is higher hardware profiling. Yeah. So here we can see that route B is like a clear winner. So and the statics are honest, and the ablation run on the same full protocol as a built-in check. Their control and root rows rerun the benchmark configuration exactly, and the tie is printed out, shows the match. The main finding is that the uncertainty weighting gives no reliable accuracy gain, and either route either route A I'm talking about, and so the fixed weight is kept for further results. You can see that the uncertainty weighting is not giving better results. We are getting same results here, and this is a different data volume. So you can see that with a different type fraction of data volume, the results is this. For deployment, I have checked, I have done this. So this is the deployment model is local execution with embedded targets. There is no API, no cloud. The deployment hybrid is quantized to int8, and its size is measured and the 20 KB of flash memory will be required, and which is 2% of total flash memory or Cortex M, if we consider Cortex M4 chip, plus 1.2 kilobytes of RAM. One interface window needs 101,000 multiples, which means 1.2 millisecond and 80 megahertz. This is 30 times less than flash memory of heavy transformers. The ONX export is 49 kilobytes, where we exported this whole model. I'm talking about that. To summarize, the performance of a small train is in 1 of the 4 seconds per fold, and the whole pipeline takes about 20-25 minutes. The accuracy cost the small deploy size stated openly in the thesis, and I said I haven't used any like LLM models like or APIs or like any other dependencies. This is like full notebook. Anyone who has this notebook and data set can reproduce each and every table or results which we can check here. Thank you.